I want to introduce Dr. Corso. He's a postdoctoral researcher here in the Aeronautics and Astronautics Department at Stanford University. He's in particular in the Stanford Intelligent Systems Laboratory under Michael Kokendorfer. That is the lab here that has the best pronounceable acronym, which is SIZZLE. He is also the executive director of the Stanford Center for AI Safety, which is broadly the topic we're going to be talking about today. His research is focused on the use of algorithmic decision-making for safety-critical applications, emphasizing the creation of robust, reliable, autonomous systems. And this is a really important topic, and obviously it's been important for a long time, and that's something that Anthony and I will talk about a little bit, but it's also something that's come to greater prominence, and we are working with Anthony to create a seminar that we'll be offering in the last week of July on this particular topic. We'll talk a little bit more about that at the end of the presentation, but if you're interested in learning more about it, there is, you should see a little button right there on your screen that you can click, and that will take you to the course page, which has a rough description of what that will look like. All right, with that, again, I want to remind you, at any time, feel free to ask your questions, but I'm going to just kick it off. Anthony, again, thank you for joining us here today. And I think probably the place to start is if you could just introduce yourself a little bit more by talking about your research.
Yeah, thanks, Pax. And it's great to be here. Thank you all for choosing to spend 45 minutes with us talking about this important topic. So I did my master's and PhD in the Aeronautics and Astronautics Department here at Stanford. And a lot of the research that I did was thinking about the ways in which we can use AI or algorithmic decision-making to improve both the safety and efficiency of transportation systems. So, something like 1 million people every year die in car accidents. And so, if we can improve the safety of things like driving cars, then we can save a lot of lives. And so the topic that I mostly studied was around, the use of AI systems to perform these tasks safely. But then the question naturally arises, how do you check whether or not you've built a very safe system? So I did my dissertation work on developing algorithms that allow you to stress test and ensure the safety of these really high stakes systems. And since then, I've carried on as a postdoc and have continued to think about kind of the areas in which we use AI systems that influence and affect a lot of people. And we really need to make sure that they are robust and reliable before deploying them.
That's great. So Anthony, I think maybe we can take a step back. So there are kind of a couple things there. And we already have a good question just about some of the terminology about what it means for a system to be robust. But I think maybe we start is can we dig a little bit deeper on autonomous systems? So you primarily worked with systems in transportation, so cars, airplanes, drones, those kinds of things. Could you talk a little bit more about autonomous systems and what you're thinking of, what that broadly covers, and what the risks are involved with those? You've already touched on it in terms of car accidents, but can you build on that a little bit?
Yeah, absolutely. So I think of autonomous systems as really any system that's going to perform a task that historically has been done by a human. So this can be driving cars is a prime example. And autonomous systems, although we've had autonomous systems for a very long time, people are becoming much more aware of them with the advent of AI and machine learning, which are techniques that allow computer systems to learn from data and basically enable us to process information in real time and enable this higher level of autonomy that we've been seeing over the past couple of years. The problem is, however, that a lot of these technologies, although they are absolutely amazing and enable us to do incredible things, often fail in kind of unexpected ways. So they tend to be a little bit more brittle than, say, humans are. So they may work in a very controlled, say, laboratory setting, but as soon as you deploy these systems and the environment changes ever so slightly, you can begin running into problems. And this is, of course, very dangerous if you're deploying these systems in a domain like driving where people's lives are at risk.
Could you, I actually have something I want to circle back onto about safety, but could we elaborate on the brittleness of some of these systems? Can you build on what that means? So it sounded at the core, it just means they fail in ways that humans might not, or is it that they fail differently than humans, or they're more likely to fail, or they just don't generalize, I guess would be the term, maybe the way humans might?
Yeah, so it can be a little bit of both. I'll start with maybe an example. So, folks showed that, for example, you can maybe if you collect data from, a certain geographic area, let's say, for maybe we're building a system that can identify pedestrians on the road. If you collect a bunch of data from a certain geographic area, and then you train a machine learning model to detect pedestrians, you're likely to build a very reliable model that can detect pedestrians really well. The problem is if you then try to deploy that model in, say, a different geographic domain where things are slightly different. So maybe the crosswalk looks a little bit different, or people tend to wear different clothes, or something like that. And all of a sudden what we see is that these machine learning models' performances can drop pretty dramatically, even though the differences in kind of the environment are quite subtle. And humans don't really have this problem. We're able to generalize fairly well across a variety of factors.
That's great. And we're already, and thank you again. I want to remind you, if you have questions, feel free to post them. We're already getting a ton of those. But I want to build on this maybe a little bit more and circle back to something before we kind of move on. Is when you initially said it, part of what got you interested is not to ensure the safety of AI systems, but the way in which AI systems or autonomous systems can improve our safety, right? So could you elaborate on that kind of the flip side? So it's not just that you're trying to ensure that systems are safer, but it's also the case that maybe AI systems can do things more safely than humans potentially in certain domains. Could you elaborate on that?
Absolutely. So like one of the reasons I'm so excited about AI in general is this possibility that we can have systems that perform, for example, much, much better than a human at a variety of tasks you really care about. So I think a great example of this would be healthcare. So if you could have an AI system that was maybe even just as good as the world's best doctor, you could deploy that system very widely across the world, providing healthcare access to people who wouldn't otherwise get it. Or likewise, flying aircraft or flying or driving vehicles. These are things that, although humans do fairly well, we can really improve the safety of, and that can be really beneficial for everyone. But of course, as soon as you start thinking in those terms, you have to be careful, because what we're talking about with AI systems is it allows it to, allows us to scale these systems out to a ton of people. And so then any risk that's inherent in the system is now a risk affecting many, many, many more people. And so we have to be extremely careful before actually deploying these systems out into the world.
That's really interesting. So part of what the particular challenge of these systems is how scalable they are, right? So if I make a mistake as a driver, I'm a single driver, right? And that potentially has local consequences, but it's not like I am driving everyone's car. Whereas what you're proposing is, or what people are trying to achieve is a system that will be deployed across all of the United States, all of the world. And so
and actually along those lines, another sort of problem that AI systems tend to face is that they can be fairly susceptible to what we call adversarial attack, or basically like intentional manipulation by people. And so, you can there's been some research where people can, for example, print out a sticker that just kind of looks like maybe a sticker you would see out in the world, post it on a stop sign, and it can make a machine learning system think that stop sign is now a speed limit 45 sign. And so this could be extremely dangerous. And like you said, it's not just going to affect that one system, but if all the cars on the road are using the same algorithm, then they can all be influenced by this one sort of attack. And so that's one of the reasons why we need to be extra careful with sort of testing and verification of these systems.
So there's one particular question I think is, maybe before we kind of move on, is there's a question about if there are additional risks for, say, big trucks or little, or different kinds of vehicles on the road. And so could you just talk a little bit about, when you're thinking about deploying these systems, I mean, how generalizable are these systems across the class of vehicle, those kinds of things? I mean, what are some of those considerations? Again, we're probably, I guess here we're talking about cars, but it could apply to airplanes, right? I mean, can the same system go in a 747 versus Cessna, and what are some of those considerations?
Yeah, so I think of AI safety as sort of like, you have to multiply sort of like the likelihood of a failure event occurring times the magnitude of the consequences of that failure event. And together that gives you sort of like your overall risk. So if you think about a system like an aircraft, which has an extremely high consequence if something goes wrong, because very bad things can happen if you do something wrong on an aircraft. So you need a correspondingly extremely small probability of failure. So the FAA, for example, tries to ensure that their systems fail no more than 1 in about 1 billion hours of flight time. So it's extremely, extremely safe, as we've all come to expect. Now, on the flip side of that, if you're thinking about deploying a machine learning model to, say, for example, serve ads to users as they come to your website, the risk of making a mistake there is relatively low. If you serve someone the wrong ad, perhaps they just don't click on the thing that you sell them, and so the risk is kind of low. So we can tolerate much higher rates of failure in domains like that. And I think that there's basically a whole spectrum here. Now, everyone wants their machine learning model or AI system to be as reliable as possible, but it becomes all the more important as those consequences get higher. And so to the question around variety of road vehicles and things like that, we have to think about, what is the domain in which they're going to be operated in. So for example, are they going to be driving downtown city streets in New York, or are they going to be driving an open pit mine where there aren't any other people around? And so the context really matters when it comes to safety.
That's great, and we're getting a lot of really good good questions. But I want to maybe before getting to some of those, I do want to I want to address something that's the conversation we're having right now is very, and where your specialty is thinking about these autonomous systems, how to build safe systems, and also how to verify the safety of those systems. But right now, obviously, one of the hot topics on Twitter around AI safety is the question of existential risk, right? Is AI going to, this is like the Terminator or Skynet scenario. Could you talk a little bit about what you're talking about and what you'll be teaching this summer and how it might or might not relate to that question of existential risk?
Yeah, absolutely. So maybe first I'll briefly articulate what I think the argument around existential risk is, and then I'll talk about how the summer seminar might or might not relate to that. So the basic idea is that, as we build more and more capable and competent autonomous systems that are more widely integrated into our society, the risk is that either due to these problems of a lack of robustness or what's often called a misalignment in their objectives. So, we ask the super competent AI system to do one thing, and in pursuit of that one thing, it maybe destroys a lot of other things that we care about. And so, this is something that people are beginning to think more about as systems get better and better over time. But the topic of my research is a little bit divorced from that, in that I think about systems that are literally on the roads today. So for example, you can go to, I think, Phoenix and San Francisco and actually get a self-driving car with no safety driver in it. You can get in that car and it will take you from point A to point B. So I'm sort of most concerned about the systems that are out there in the world today. But what I will say is that many of the problems that exist in these systems, like a lack of robustness or security flaws and things of that nature, could exacerbate this problem of existential risk down the line when we have more and more concrete systems. So I think thinking about these problems early on is really important to kind of mitigating those risks going forward as well.
That's great. And this is kind of, again, on that high level, at this level, where does ethics, this is a question that came in earlier from one of the participants, where does ethics come in, or that question, how do you consider that or think about that? Or is that maybe at a level up from these very concrete sort of technical problems that you're trying to address?
Yeah, so that's a fantastic question, and it's an extremely important piece of the whole deployment of AI systems, ensuring that these systems are deployed in a way that's equitable and fair to all groups. And in fact, you can even think about the risk that, say, an AI system will behave differently at different subgroups of people based on gender or race or something like that, as essentially a lack of robustness to various subgroups. And so this is a problem that we absolutely need to mitigate. It's a problem that comes from the data sets that we as humans have generated. We have bias in our society, and that to show up in the data sets that we create. But it can also be issues with the model, models that we use to train on those data sets that will pick up on spurious correlations and things of that nature. So, so these are the types of problems that we need to address, and that we'll be talking about in the seminar.
Can we dig on a little bit deeper on those? We're getting a lot of really great questions, so I'm just going to summarize it. So there's a lot of questions about kind of specific applications, particularly around, say, use in warehouses or industrial machinery. So I think maybe we can come back to that in the end. But my sense is some of what you're working on applies across these kinds of machines. So though your expertise is really in working with self-driving cars, with aviation, with airplanes or drones, my sense is it applies across the kind of fundamental theoretical concerns that you're addressing do apply across those domains. Could you actually, before we do that, could we then perhaps take a step back and you've already articulated it, but maybe articulating it again. So there are kind of two aspects to this, right? There's building and there's verification. Is that correct? Could you just elaborate? And you just touched on that. So could you elaborate, when you're thinking about designing an AI system, what are the kind of steps or the different aspects where you're thinking about safety and just building out on those?
Yeah, absolutely. That's a great question. So first, to your original point, I do think that a lot of what we're about to talk about here basically applies across all sorts of application domains, because a lot of the core underlying technology is very, very similar. So yeah, as Pax mentioned, you have two phases, I would say, very broadly speaking, when designing an autonomous system for a high stakes application. The first is just building that system. And so when we build that system, we have to kind of do a variety of things to ensure that we're building kind of the best possible system. So maybe that means we're collecting data, making sure we have enough data, or our data is diverse enough to cover all the aspects of the problem we're trying to solve. We need to ensure that we're using kind of the latest and greatest methods, engineering methods that are known to kind of behave in a safe or more reliable way. And then once we've done that, so maybe we've created a system that we think is very safe because we've used all of the practices, we've collected data, we've done some preliminary, experimentation, and things seem to be going well. But the second phase of this, before deployment, is we really need to understand what can go wrong, and what are the risks if we deploy it. And this can be a whole separate challenge. So I'll actually give a sort of a short anecdote to illustrate this. So my advisor, Professor Michael Kuckendorfer, helped develop the next generation of aircraft collision avoidance. So these are systems that are on board all commercial aircraft that basically ensure that if there's the potential for a mid-air collision, that it alerts both pilots to make a maneuver to ensure that that does not happen. And so he started working on this project, I believe around 2011, and they built prototypes of it, and they designed an extremely safe system. But it took an additional 8 years of verification and validation to build enough trust in that system to get the FAA's stamp of, and this is already when the system was safe enough. They just had to ensure it, they had to build the trust in it in order to make sure everyone was confident that what they were deploying was going to actually be safe. And so both of those aspects, the designing of the system and the test and evaluation, are both crucial pieces of eventually deploying a safe system.
And we're going to get into this when we talk through the class, but can you talk a little bit more about the verification piece? I know you've done a lot of work around that, really interesting work around formal verification, as well as, I'm going to get this wrong, but is rare event or robust training. So could you talk a little bit about, maybe focusing on your research, but the kinds of things that are important for verification, both to ensure that a system is safe, but also and we got a question about selling AI, but that's kind of related to your last point, but also in communicating or showing and demonstrating that safety to people who might be using it.
Yeah, that's a great question. So I'll talk a little bit about my dissertation work because it's very near and dear to my heart. And so this is around, basically the analysis or the testing of extremely safe systems. So for example, if we're designing a self-driving car, we want to make sure that self-driving car is much, much safer than a human. So for example, maybe we want it to be 10 times safer than the average human driver. And what that means is that this will have basically a failure rate of something less than 1 in 10 to the 7. So 1 in 10 million chance of say, causing a collision for every hour on the road. And so this poses a real challenge because, if I make a system, how do I know that it's going to fail only 1 in 10 to the 7 rather than 1 in 10 to the 6? I would have to drive that car hundreds of millions of miles to ensure that it was hitting that correct level of safety. And so this is the problem that we call in sort of the research community, the problem of rare events. So these failure events are extremely rare. And if we were to just sort of naively go throughout our day, maybe simulating our autonomous vehicle in sort of nominal conditions, we're very unlikely to encounter these failure events. So the focus of my dissertation work was around how can we actually increase the likelihood of encountering one of these failure events. And the way we did this was actually handing control over the environment. And the environment in this case would consist of maybe pedestrians on the road, other vehicles on the road, maybe weather and lighting conditions, things that could affect the performance of our automated vehicle. And we would hand over those aspects of the environment to another AI agent. And that AI agent would be trained to try to uncover failures of the system. So it would actually try to manipulate the environment in such a way as to cause our autonomous vehicle to fail. So it's kind of, a little bit backwards. We think of AI as, doing what it can to say avoid collisions or something like that. But this was using AI to actually discover the weaknesses of our automated vehicle. And when we do that, we can uncover a whole bunch of possible failure modes. And when we do, we can basically allows us to understand what are the weaknesses of our system. Are we okay with the failure modes that we found, or do we need to go back to the drawing board and fix some of these issues before we deploy it?
And that's great. And so, so there's this kind of the question, you've got rare events, you're going to be testing something that's so safe that in theory, that, the kinds of events that cause a failure are really, really rare. And so how do you uncover those before they happen? I'm assuming this could also, in theory, be applied to non-AI systems, right? I assume a similar model could be used to stress test structures, to stress tests, not stress tests, but to test the modeling of a structure or just the design of a mechanical system.
Indeed. So you definitely could do that. The difference is that oftentimes in more traditional systems, you don't need this approach because you can reason about the safety of the system from sort of first principles. Like, what it's made up of. Maybe it uses GPS. We know the characteristics of GPS. We can kind of reason about its safety in that way. The difference here is that now these, say, autonomous vehicles are based off these very complex machine learning components, which are these black box models that are very difficult to reason about. And so we need to kind of begin coming up with other ways of testing these systems. And what I described is one way.
That's really interesting. So again, I'm going to call it, and this is not technical because I'm not technical, the kind of traditional systems, you can reason, as you said, from first principles. We understand the physics well enough of this mechanical system that we can predict the failure points. With an AI system, we can't reason about it based on first principles. So we need to test it in simulations. Could we build on that? Because I know Michael's lab has also done work around formal verification. Could you tell us a little bit about that, what that means, and how you're using that, or how people could use that to test systems?
Yeah, absolutely. So formal verification is just like a fancy research term for mathematical proofs. So what we're doing in formal verification is trying to construct a mathematical proof that the system has the safety behavior that we want it to. So for example, we might try to construct a proof that our vehicle will never collide with another vehicle. Now, this may sound challenging, and it is. And oftentimes what's required to do these formal verification proofs is to make a bunch of assumptions. So we'll assume that pedestrians can only move so fast and that they'll only move in a particular direction, and so on and so forth. And so we make all these assumptions, and then we prove that our system, under those assumptions, will never, ever be involved in a collision. Now, the problem is, number one, that if those assumptions are ever violated, then we no longer have those guarantees. But that could be okay, because at least we know we're safe when the assumptions are holding, and then when the assumptions are violated, we can, perhaps take some evasive maneuver or identify or alert someone that there could be a potential problem. And so that's what we mean by formal verification, and it's been a really useful tool to basically proving properties of various components that have gone into aviation systems as well as autonomous vehicles to kind of provide a boundary over which we know we are safe, and that can be really, really useful.
That's fantastic. Yeah, and I think those are two really interesting things. And I should point, we have a link to Anthony's bio there, and so if you want to dig in deeper, I think there are some links to your CV and some of the papers that you've published, or also to the CISL, the Stanford Intelligent Systems Laboratory as well, if people are interested in sort of digging deeper into some of those topics. We're getting a lot of good questions, but I think maybe we can actually circle into and come back to some of these questions, but I want to circle into the course that you've been planning and trying to develop for this summer. And so maybe you can just walk through, because I think in walking through that, you're going to be expanding on this conversation we've been having and talking about kind of what goes into building a safe and verifying a safe system. So can you talk through what you're thinking about in terms of the content? This is a short 1-week class, right? So it is technical, but it's obviously, it's not a semester long or anything like that. So could you talk a little bit?
Absolutely. So the reason I'm putting together this course, maybe I can start there, is because I think that there's a lot of great resources out there on the internet through SCPD, for example, where you can learn about how to apply machine learning and AI to solve a variety of problems. And I remember taking one of these courses several years back and thinking, wow, this is really incredible. I can't believe how sort of straightforward and easy it is to apply these techniques and solve real world problems. The issue is that in the years since then, and I've now built a lot of machine learning systems and AI systems, you begin to discover that the devil is often in the details. So there's a lot of issues that can go wrong when you actually go to try to deploy or build a system for a real world problem. And so I've kind of collected, a number of learnings from my years in doing research in this topic. And I wanted to put those learnings into kind of one place where someone who's maybe taken some machine learning courses can go to get up to speed on kind of the latest kind of advancements, but also current issues around AI and machine learning. And so to that end, we've outlined basically a 5-day course. Each day will consist of about 2 hours of lectures. On the first day, we're going to be talking about sort of an introduction to the use of AI in safety critical domains. And I'll walk through some examples of times where AI has failed or machine learning models have failed. And then talk about how, what are some of the techniques that we can use to build much more robust machine learning models that don't suffer from some of the problems that we've seen quite so much.
Can you define robust a little bit? That was one of the first questions.
Oh, yeah,
what
absolutely.
What does robust mean?
So when I say robust, what I mean is that the model will, or an AI system will have similar performance even when the environment in which it's operating in changes ever so slightly. So like I said, a robust model, say for autonomous driving, will do just as well in the morning as it does in the afternoon when the lighting conditions are different and people's behavior are slightly different. That's what we mean by robustness. Great. So then and the next 2 days will be around model evaluation and verification. So on the next day, we'll be talking about techniques for explaining these machine learning models. So as I said, often these are very complex neural networks that have, billions potentially of parameters that are used to process images. And they're often thought of as too complex to really think about. But people have been developing ways to sort of peer inside the black box a little bit and try to understand a little bit more about how these machine learning components are arriving at the decisions that they have. We'll also be talking a little bit about this question of failure identification. So using these sort of adversarial techniques to kind of stress test your system to uncover the ways in which it might fail as a tool to kind of eventually build safe systems. And then we will be talking about methods in formal verification as well. So certifying or mathematically proving that our neural networks are resilient to, say, adversarial attacks and have other properties that would be desirable. We'll get to play with some libraries that people have developed to do this, so you can actually use it in real-world projects that you might be working on. On day 4, then we're going to move into a discussion on uncertainty quantification machine learning. So I'll say a little bit about what I mean. So uncertainty quantification is basically, what happens when your machine learning model, say, encounters a situation it's never seen before. Would you want, on the one hand, for it to just decide what it thinks is best and go forward full steam? Or would you want it to identify the fact that it's in a novel situation and perhaps maybe alert a human supervisor or basically do something that it knows to be. And in the latter case, that's the use of uncertainty quantification, where it's uncertain about what it's doing. And so, you put on the brakes and make sure things are okay. And so there's a bunch of techniques for building this style of reasoning about uncertainty into the machine learning components or the AI systems that you build.
So Anthony, just to pause you there. So the uncertainty quantification it's the idea you're in a new or novel situation. It's one, recognizing, I suppose, is probably a problem, yes. Just recognizing it's a new situation. Yep. And then 2 is knowing how to respond to that. And it can be, we think our system is still reliable in this, or it's alert a human, or I don't remember if this is something that CISL works on, but it could be something like reverting from the the AI system to a model that's much safer, or to a safer parameters or something like that.
Indeed, yeah. Often these systems are built with like what they call fallback strategies. So like if everything else goes wrong, we have a fallback strategy that we know to be safe, though it's going to be much less effective than your AI policy. But the real challenge often is identifying the situations that are novel. You would think that this should be, again, something easy to do because humans do it very regularly. We know when we're in a situation that we don't understand. But machine learning models have kind of a bizarre attribute where they may be extremely confident in decisions they're making, even though it's very uncertain and they're wrong. So there's there's potential for major downsides if you don't take this into account explicitly.
That's great. I'm sorry to interrupt you. I just thought that was one worth digging into a little bit more.
Yeah, and happy to answer more questions about that. And then we'll kind of tie it all together on the last day, where we'll talk about, for example, the aircraft collision avoidance system that I mentioned earlier. We'll use that as a case study to think about, how you put all these pieces together in a way that can build a very reliable system. And then I'll talk a little bit about some of the upcoming regulation around AI. So there's actually some, there's a big law that's soon to be signed in the EU, and then there's been some discussions here in the US, and thinking about the ways in which AI might be regulated and how some of the techniques I'm describing perhaps will fit into that regulation, because you might be required in the future to do many of the things I'm talking about to ensure that people stay unharmed from the systems that we build.
Thanks, Anthony. So it's a really interesting course, and again, it's focusing on kind of these autonomous systems. I guess one thing is, do you see? So we're talking in the primary use case we're talking about is autonomous vehicles like cars or aviation. We got a lot of questions about working in warehouses, maybe industrial machinery. Does this still apply? I mean, in some sense, that's a much more controlled environment than a road where you have pedestrians, where the entire kind of infrastructure is not built around AI. Whereas when you go into a factory, the infrastructure can be designed around the systems themselves, right? And so I guess broadly the question is, how do these apply to those kinds of systems that are or situations that are more controlled? Do you think it's still applicable to people who are interested in machine learning and industrial applications?
Yeah, absolutely. So I think, almost everything will apply. So, I mean, it just to varying degrees. So as you mentioned, in the autonomous driving setting, you're in a very open and uncontrolled environment. So lots of stuff can go wrong. Lots of things can change over time. And I think it's one of the reasons why it's taken such a long time to get autonomous vehicles out on the roads operating safely. In a much more controlled environment, you do have the luxury of perhaps controlling the environment in which the AI system is operating in. But it's never so straightforward as that. Things will always change, and you want your AI system, say that's controlling a robotic arm, to be somewhat resilient to the small changes that occur on the factory line or changes to the environment, lighting conditions, seasonal changes, things like this. You might, for example, not be so worried about I talked a little bit about what I called adversarial attacks, whether there's some sort of intentional manipulation or AI system. Maybe that's less of a concern in the warehouse domain than it would be in the driving domain. But nonetheless, you still want to have as robust of a system as possible in both of those applications. It's just sort of to varying degrees.
That's really interesting. How do you even, I guess in one sense, one question to follow up there is, how do you reason? I mean, do you reason from first principles? You talked about using AI systems to kind of play an adversarial role in manipulating a simulated environment. How do you even figure out what parameters in that environment to sort of adjust? And as you're talking, one thing that comes to mind is, say you're working in a warehouse, and say that warehouse, it has windows, right, that are facing.
Yeah.
You might not think, you wouldn't necessarily think about daylight or nighttime conditions being a significant factor, but it could be. But how do you approach even thinking through what the environment is and what are the important changes to control for or to test for?
Yeah, that's a great question, and there's no easy answer. It's going to be a combination of the experts in the domain, so people who have worked in the warehouse space before, and they understand what things might change, what are the common kind of situations that might arise that maybe would be challenging for a human to handle, and then you can infer that it would also perhaps be challenging for this AI agent. You can look at a bunch of examples, and this is what we'll do in the course. We'll look at a bunch of examples where you have these what we call distribution shifts. So this is where things in the environment change ever so slightly, and the machine learning model's performance drops quite a bit. And so we'll look at a bunch of examples of that. And you'll see, for example, changes in lighting condition or color scheme, like things like this. So you can build a little bit of an intuition around what types of factors may influence certain types of machine learning models. And then the last piece of this is like you absolutely need to monitor your systems as you deploy them. So you don't know everything that's going to arise. And so it's really important to build in this element of, number one, quantifying your uncertainty during operation. So like, as we talked about, making sure the system is aware when things change and can potentially alert, say, a user. And then also having systems that are monitoring the performance of these systems over time. And if you see the performance dropping, for example, then you know something has shifted. Maybe it's time to retrain your model or intervene in some way.
That's great. So maybe even revisiting when I had talked to you, when I had mentioned earlier, kind of the aspects of it. There's building, there's verification, and then is monitoring almost maybe a third thing there, right? You're verifying it in advance, and then once it's deployed, is making sure you have, and this is what you're talking about in terms of uncertainty quantification. You're building into that system a way to monitor, to flag situations that are outside what would be normally considered, what would be considered normal.
Yeah, so that's like one aspect of what we call runtime monitoring, is that uncertainty quantification piece that can alert when something has gone off nominal. But another thing you can do is just every so often, every week or something, reevaluate your say model on a new set of data. So it's sort of like just a repeated validation process. So doing the same thing you did before you deployed it, just on an iterated basis to ensure that things are staying at a high level of performance.
So this would be, so in other words, the AI system is running, it's doing its thing. It's not retraining itself as it's doing it. It's not, so to speak, learning in the environment. But what you're doing is collecting more data, then retesting it on the new data.
Exactly.
Yeah. This is a little bit of I just find it as a really fascinating idea, and it's related to that is this idea of I think it's called distributional shift is what you've talked about. So I guess the idea is it's related to uncertainty or novel situations, but it can also be that maybe the AI system is working well, but say the camera that's recording it is degrading, and so the quality of the image is changing. Can you talk a little bit about that and maybe this idea of distributional shift, or maybe I'm focusing on the wrong thing, but just how that can affect the safety or the continued operation of the machine? It might not just be changes in environment, it could be changes in the sensors, I guess.
Yeah, absolutely. So it could be changes in the sensors. And I've talked a lot about sort of these physical changes in the environment, like, changing lighting conditions and things like that. But distribution shift can be something that happens, say, like imagine, for example, that we have an AI system that's helping you diagnose new diseases at a hospital or something. What would you think would happen to that system at the beginning of the COVID-19 pandemic, for example, where a new virus altogether has shown up on the scene? It would make these systems go haywire because they've never seen that before. And so it can be things like that, where like the distribution of inputs that it's seeing is shifting because of a new thing in the world or something like that.
Interesting. Yeah. So it's a completely new, right? I hadn't even thought about that. If there's a new disease or something like that that's introduced, it could completely change the way it's diagnosing everything. That's really, that's great, Anthony. And we're nearing the end of our time. So maybe, we've gotten a couple questions about this. So maybe if we, in these last couple minutes, we could do just a kind of a big kind of zoom out and away from kind of the specific things, and just maybe get your thoughts on what the future of autonomous systems are, what you're hopeful about, and what you're worried about.
Yeah, absolutely. So as I said at the top, I'm really hopeful that the use of that AI systems can basically do a bunch of things that humans historically have done, so they can do them perhaps more quickly, more efficiently, at a larger scale, and this can bring a lot of great resources to a lot of people. So I think that's like the thing that everyone is shooting for. But there are ton of risks. And I think, something we haven't even talked about today, though I'm sure everyone has kind of encountered it recently, is things like ChatGPT. So these generative AI systems that are able to produce content, text or images or videos and things like that. And these types of systems, when deployed without much oversight, can lead to very strange and bad things happening. So they can exhibit toxic behavior. They can discriminate against people. They can, steal people's like copyrighted information. Producing images that are in the style of an artist or something like that. They can be used to intentionally produce misinformation, and they can do this at scale, like we talked about. It's something that a human typically does, but now you can do it incredibly fast and widespread. So I'm a little bit worried that especially generative AI systems are being deployed very widely, very quickly, and we're not exactly sure what kind of influence it's going to have on our information ecosystem. So now there's a ton of AI generated content out in the world, and it's not always so obvious when you're interacting with it. So that's definitely one of the concerns that I have.
Do you think that this course, so coming back to the course, do you think that some of these principles could also apply to people who are thinking about something? We were talking about cars and machines, things that are interacting with the physical environment and humans. There is, is that something that you think some of these principles can apply to something like ChatGPT? Can you do testing for kind of emotional harm to humans? I guess it's a tricky question. It's much less, I think you called it a less tractable problem, maybe.
Yeah. It's much less cut and dry because it's not clear. So these systems are very general purpose. Like they can do a lot of different things. Whereas the systems I was describing earlier have like sort of one task that you can kind of check its performance against. And so, so I think many of the techniques can and will apply to things like ChatGPT, but it's just a more challenging domain because, it's very difficult to quantify like the harms on a societal scale and all of these things. But I think, still you want for example, you want ChatGPT to be more robust and that its behavior shouldn't substantially change when it's interacting with people. You would want it to express uncertainty when it doesn't know something. Sometimes it does. I don't know if you've seen it. It'll say, "Oh, I'm not sure about this." And you would want it to be truthful and honest and things like that. And so I think in principle, many of these techniques apply, but it does get a lot messier when we're talking about these really large scale generative AI systems.
Do you foresee these generative AI systems being applied in domains like autonomous vehicles, or does that itself pose too great a safety risk? I'm sorry, now we're going a little bit off.
No, it's fine. I certainly hope not that they are not, because it's, I've seen so many examples of failures of reasoning, failures of logic with these systems that we don't want to put them behind the wheel or behind the aircraft. It's possible that, if we, 5-10 years from now, as these systems get better and better, they will be more human-like in their reasoning capabilities and therefore could be trusted to do something like this. But we're definitely not there yet. And I think it's really important for these tasks that are safety critical and have high stakes that we still stick with the kind of systems that have been designed for this bespoke purpose, not these general AI systems.
Well, thank you, Anthony, for joining us today, and thank all of you who joined us today for this fireside chat with Anthony. Though there's no fire, I guess the Zoom side chat, the online side chat. Well, thank you again, everybody. Thank you, Anthony, and we really appreciate your time. And maybe we'll see you again soon.
Yeah, thanks, everyone. Appreciate it.